We are recording, so that means we are ready to start concept set 8. This was a concept set that I added after the fact because I realized that I had nothing talking about the electronics of the robot that we will actually be writing code for. So I added this little slideshow to the whole process to make sure that um, we covered the general basics of robot electronics. We won't go into the nitty gritty of how electricity works or anything like that. We're just talking about the different components, the different things that you might run into when you're working with specific types of electronics and trying to write code for them. Now, this is more oriented towards electronics, so we won't talk a lot about programming for these devices specifically this evening, but um, future sessions will contain more about how to write code for the different things that we talk about. One thing to mention that will be a little bit different about this one is all of the programming videos so far um, have been unlisted in an unlisted playlist. Um, this video specifically won't be unlisted. I plan on making this one public. I haven't decided if I'm going to unlist the programming videos. As I've mentioned in the past, every year that I do programming, I always end up hating some aspect or subset of aspects about how I've done the programming training. And so it tends to steer me more towards not releasing them. Some of them I have, some of them I haven't. This video in particular is going to be pretty straightforward. So my plan is that I will make it generally public so that anybody looking for basic FRC electronics can come and look and, you know, watch the video rather than having to have the link, which I tend to only post in the Discord. But with that being said, unless there are any questions, let me get a share going. All right. So the first thing I want to talk about is why do programmers need to understand electronics? Uh, this will be the only slide that is very, very programming oriented before we actually start talking about electronics. Java in of itself is an object-oriented programming language, meaning that you're representing real-world things in most cases that have different characteristics and behaviors that you will interact with when you're writing code. Um, without understanding what something is, like if you've never seen a Talon SRX before, if you don't know what a power distribution hub looks like, then it's going to be more difficult to be able to write software to control that thing. So with this, my plan is to give a relatively brief overview of each item, talking about some things more than others, and hopefully giving a general overview so that you know when someone says, we need this Talon SRX to do this thing, we need this Spark Max to do this thing, you'll have an understanding of what that thing is and how it generally will interact with the robot. So the first thing that makes sense to talk about is the RoboRio and the RoboRio 2.0. This is the brain of the robot. It's more or less like any other computer. It has a CPU, it has RAM, it has storage, it has USB ports, Ethernet, that sort of thing. But it is generally attuned to being used for either industrial or robotics applications. Because of that, it runs an operating system that, is unlike Windows or Linux or Mac OS. It runs a real-time operating system called NI Real-Time Linux. We won't talk too much about that, but it is an operating system. It has some of the common facets of an operating system. It obviously can't do graphics. Like there's no VGA or HDMI port that you could connect to actually see like windows on a screen. But it is in of itself just a computer. What you may not realize is the RoboRio and the RoboRio 2 have some comparatively underwhelming specs, and you can see the table on screen if you want to review those. The RoboRio 2.0 is a slight bump, but in general, the RoboRios themselves don't have a whole lot of computing horsepower or a whole lot of RAM. And it's done this way because really, in the grand scheme of things, for what they're doing, they don't need it. And we'll get on into that a little bit more on the next slide. But in general, the RoboRio is multiple magnitudes slower than like your average cell phone or laptop computer. It just doesn't have the sort of pure grunt of a normal CPU that you might have in an everyday device. Part of what makes the RoboRio able to do what it is able to do is because the CPU has something called a field programmable gate array, an FPGA attached to it. The FPGA is there to do things that your average everyday CPU couldn't do. So for example, the FPGA is able to maintain nanosecond timing and perform things like PWM generation, which we'll get into what PWM is a little bit later, but it's basically a very high frequency on and off signal. But as I mentioned previously, of course, the FPGA doesn't solve all the problems. And while it does do a lot of work that the CPU in of itself couldn't do on its own, it still doesn't take away from the fact that the CPU itself is, dual core 667 megahertz or 866 megahertz. It's still relatively slow. With that being said, there are some teams that will actually put an additional device, usually an additional computer like a Raspberry Pi or something similar, on their robots to do things that require more intense processing. That conversation is a little bit out of the scope of this particular training session, but it is possible to have alternate devices on the robot that can do more intense processing for things like machine learning and vision tracking to take load away from what the RoboRio would ultimately have to do, in addition to controlling your motors, reading values from sensors, running LEDs, that sort of thing. The next thing we're going to talk about is some of the different I/O input output that is available on the RoboRio. If we actually jump back a couple of slides too far, you can actually see on the left and the right sides and the bottom side of the RoboRio, there's a whole bunch of like pin headers. And this is sort of the broken out I/O, the things that are available to you to control different things on your robot. And we're going to talk about most of these things individually on their own slides. So let's jump back over there. So digital I/O, digital input output, is used for things like switches and buttons. Specifically, the input portion is used for switches and buttons. So for example, on my robot, the big red button, the big friendly button that I normally use for like bump testing. So when the robot runs into something, that's just a switch, a button. And that uses a digital input. Some of the encoders, which we'll talk about in a little bit, like the things that we use to measure the speed at which a motor is rotating or the distance that a system has traveled. Some of those encoders also use digital inputs. Along with digital I/O is you have pulse width modulation. And basically what this is it's a way of conveying information by varying the frequency and when you have a particular digital signal on or off. So you can increase or decrease the frequency, the number of times per second that you can make a pulse, and then you change how often a pulse is made. Maybe you do no pulse for a while, and then you pulse one, and that means something, and then you do no pulse for a while, and then you pulse two, and that means something else. PWM can be used for a few different things in the robot. It can be used to capture sensor information, or it can be used to control motor controllers. The controlling motor controllers thing is a little bit more legacy. It used to be that the vast majority of the motor controllers that we had available to us could only be controlled by PWM. So you would have 10 to 20 different PWM connections, all branching to their own motor controllers, splayed out all over the robot, and it tended to get a little bit chaotic. There is an alternate system that we use now, which we'll talk about later, that's called CAN. But you can still use, with the vast majority of motor controllers that we have available to us today, you can still use PWM to control them. It's just not done as commonly because there's other ways of doing it now that are quote unquote better, I guess. The next thing we're going to talk about is analog in. Digital signals are either ones or zeros, on or off. Analog values can be represented by a wide range of values. Usually the measurement is done by way of voltages. Analog in tends to be used for sensors in general, and it is used with things like time of flight, so measuring distance based on like emitting a high frequency sound and waiting for you to hear that sound return as it reflects off a wall, and potentiometers, things for measuring angles. One good example of a potentiometer is in most vehicles, the volume knob is a potentiometer. And it's just used to determine how loud the music is, how loud whatever you're listening to is. Analog in, again, depending on what you're trying to do, you may be using it, you may not be. If you had like an arm or something and you were trying to determine what angle the arm was at, using an encoder for that application might be a little bit challenging, but a potentiometer, where it has a fixed number of degrees that it can measure and it will always be accurate because it's based on a voltage, might be a better solution type of thing. I2C and SPI. I2C is inter-integrated circuit. SPI is serial peripheral interface. These are two types of communication mechanisms that are integrated with the RoboRio. They both work differently from each other. They're not interchangeable, but they both serve to communicate with sensors or other devices on the robot. So for example, I2C, one of the most common uses of I2C in FRC would be to use something like the rev color sensor. And SPI, one of the more common uses is for gyroscopes. For example, there's one in particular that was distributed to teams for years, made by Analog Devices, I believe, the ADXRS 450. And that just plugs into a port on the upper right-hand corner of the RoboRio, and it uses SPI for communication. Each of these mechanisms have their benefits and their shortcomings. And usually any one particular sensor will implement one or the other. It is also possible to control certain motor controllers with SPI. I'm not aware of any that can be done with I2C, but there are motor controllers that can be controlled by SPI. I've never heard of a team doing that, just because, again, it's one of those things where the setup is simpler with another communication mechanism that it doesn't really make sense to do. So in most cases, you're just going to see I2C and SPI used for sensors. So the next thing that we're going to talk about is CAN, and CAN is that thing that I've been referencing when talking about PWM and SPI. CAN, Controller Area Network, was originally developed for the automotive industry. If you've ever seen a vehicle get worked on, you may see the automotive tech come up with this big chunky tablet looking thing with a really long cord sticking out of it, and they plug it into your car and they use it to read codes off your vehicle. That device is communicating with your vehicle over CAN. It is asking the computer via CAN, what the heck's going on, what's broken, type thing. We use CAN for robotics, for interfacing with motor controllers and sensors. And because CAN is a bus, we can use just 2 wires, usually they're colored yellow and green, to communicate with many devices, just with 2 wires. Every device on the network will have its own unique ID, 0, 1, 2, 3, 4, 5, 6 type of thing. And that is how we send messages to that device over the CAN network. Now, recently, especially with the boom in robots that use swerve drives, some teams are running into issues where they are actually maxing out the RoboRio's CAN bus. The CAN bus is relatively speed limited. It is slow, generally speaking. And so what teams are running into is they're saturating the bus and they can't get any more messages out, and it's causing degraded robot performance. And there are ways around this. A lot of teams have been doing experimentation to try to find the best ways to reduce overall CAN bus utilization. But generally speaking, if you have less than 15 to 20 devices on your robot that are all connected to the CAN bus, you should be more or less okay. Once you get above that 15 range, depending on what you're doing, you're apt to run into issues. But it all depends on what you're doing, what sensor data you're retrieving, how many motors you're trying to control, and when, type of thing. So it's kind of a toss-up who has issues and who doesn't, and what needs to be done to resolve those issues. The next thing we're going to talk about is the MXP, the MyRio expansion port. It's the long bar in the middle of the RoboRio that has a bunch of pins in it that are unlabeled. And it's used to give somewhere for add-on boards to plug in to add additional functionality to the RoboRio. There is a bunch of stuff on the MXP port, additional digital I/O, PWM, analog input output, and along with that, there's an additional I2C port, an SPI port, and a serial port as well. Every year in the rules, there is a list of approved MXP devices that can be used with the RoboRio every year. New devices are added periodically, either when old devices get upgrades or when teams or companies submit to have their design approved for general use. It is also possible for teams to create custom circuits that interface with the MXP and still technically be legal, because there is a provision for custom circuits in the rules. Again, that's a more high-level topic, and generally speaking, mid-tier and lower teams can get away with not interacting with the MXP at all. Even some high-level teams, I'm certain, probably don't make use of the MXP for any one reason or the other, because they found other ways of accomplishing what they want to do. Now, before I move on, because we're going to switch away from talking about the RoboRio and its I/O and its ports, and start talking about some other devices. Are there any questions? And I know I keep looking this way. My camera's over here, and what I'm reading is over here.
Can the MXP port be used for something other than, like, can you just program like straight DIO and use it for that instead of for custom PCBs?
Yes. the MXP is just additional I/O. Um, it's all tied into the same limitations of the rest of the I/O on the system. Um, so like there's a certain number of PWM generators available on the FPGA. So like the MXP doesn't necessarily enable you to like use an exorbitant amount more. I think it allows for like 6 more. But at that point, like what are you doing with 16 PWM necessary devices? Like
Yeah.
that sort of thing. Um, Generally speaking, the MXP is just a convenient way of connecting via a common recognized port. The pinout is commonized so that, if a team doesn't have PWM port 0 and 1 open, but that's the only way your device fits, it doesn't work, sort of thing. That's a really bad example, but that's the only one that I can come up with on the fly. But you could feasibly, just use like regular old female point, 0.1 millimeter header connectors and plug right into the MXP, and it's, as long as it follows the custom circuit guidelines, you should be okay. And the custom circuit guidelines can be a little vague in the rules, in my opinion. Of course, that's my opinion. But generally speaking, as long as you're not trying to control a motor and you're not using power over an amp type of thing, you're probably fine. But of course, anything you design before build season that interacts with the MXP to be used on a robot in competition would have to be open source, public type of thing. So there is that particular issue to think about as well. Any other questions? Okay. So next, what we're going to start talking about is power distribution and how we move power between different components on the robot. The first thing that we're going to talk about is the root of where all power comes from on the robot, and that is the PDP or the PDH. The PDP, power distribution panel, and the PDH, power distribution hub, are used to manage and monitor the power connections on your robot. Excuse me. All of your devices must be in some way connected to the PDH, PDP. All power has to come from here. The battery comes into this, and all power comes out of this. The PDH and the PDP have the ability to report power usage. Some teams use this to detect current spikes and make programmatic decisions on whether or not they should do one thing or the other with a particular motor. But for the most part, this information is used diagnostically by people like CSAs. You can see my orange hat behind me, to sort of identify where problem systems might lie and what might be overdrawing power, causing fuses to trip, fuses to pop, breakers to trip, that sort of thing. To talk about the differences between the PDP and the PDH very, very quickly, the PDH is newer. It's made by Rev. The power distribution hub is newer. Both of these will be legal for the foreseeable future. The PDH does have more ports and more flexibility of how much power you can draw out of each port. The PDH also has some additional convenience features that have cropped up simply because it's supposed to be an improvement over what cross-the-road electronics made with the PDP, the power distribution panel. And of course, if you aren't aware which one is which, the panel made by CTRE is the black one on the top with the red and black sort of openings. And then the bottom one with the orange little levers is the one made by Rev, and that is the PDH. The only thing that I will say finally about this is the PDP or the PDH must be connected to your RoboRio via CAN regardless of whether or not you're going to be using the features in your code. And the reason being is because we need to be able to see that diagnostic information from those devices if you're having a problem with your robot at a competition. So it's not optional. You will always have at least one CAN device on every robot, and that is the PDP or the PDH. To continue with these two devices, all of the PDP and the PDH devices are fuses or self-resetting breakers. These are used to help prevent massive overdraw on any particular channel, which could damage components, could hurt somebody, that sort of thing, cause a fire. So you'll see either the little black snap action self-resetting breakers, or the colored, because they're all different colors for the different amperages, the colored rev versions. And each channel, and a channel, if we look back at the last slide, a channel is one set of red and black connections. It's a little bit easier to see on the rev model. The white sections with the slot denote one channel. Every channel must have the appropriate fuse or breaker installed. If they don't, if the channel doesn't have something installed for a fuse or a breaker, it simply won't work. Both of the devices do that. They just simply won't provide any power. There is a indicator LED on each channel that if you try to pull power from it and you don't have a fuse plugged in, I think they both blink. I think they both blink red. But I can't remember off the top of my head what the PDH one does. But the PDP is a red LED that glows if something is plugged in without the appropriate fuse or breaker. Generally speaking, every channel should only have one thing plugged into it. There are some exceptions to this rule, but for things like motors, general consensus is that one motor per channel. There are some motors where you can get away with it through specific rules, but in general, you should only have one motor per channel. The next thing that we're going to talk about is the PCM or the PCH. The pneumatics control module or hub is used to control pneumatic cylinders and compressors. This is a separate device that connects to your robot via CAN that is used specifically for managing compressors and the solenoids that make air-based motion happen. Both the PCM and the PCH can drive either 12-volt or 24-volt solenoids. This is important to know because if you have one of these devices in 24-volt mode and you plug in a 12-volt one, it will let out the magic smoke. You'll burn it up. It'll be dead basically immediately. And solenoid modules are not cheap. Single solenoid modules tend to run $40 to $50 a piece, and then double solenoid modules tend to be like 60 to 80, depending on what you're buying and where you're buying it from. So just something to keep in mind. The newer model is the PCH, the pneumatics control hub that was brought on by Rev. The nice thing about the PCH is that rather than just using digital pressure sensing, like knowing when the system is full versus when it's not full, it actually adds analog pressure sensing. So you can actually have a pounds per square inch, a PSI value. And so you can make more educated decisions about when you turn your compressor on or off. And the reason why you'd want to do that is simply because starting and stopping a compressor many times tends to use more power than just starting it once and letting it run. And it's because spike amperages tend to be exceptionally high compared to just running it consistently for a long period of time. On top of that, the spike in draw can cause robot performance issues where motors will feel sort of laggy as the compressor comes on, because the motors and the compressor itself are fighting for the available energy on the robot. And if your battery is getting weak, that process of fighting causes them to have to kind of share what's available, making things feel laggy. We're now moving on to my least favorite thing to talk about, and that is the current state of the robot radios in FRC. Currently, the Open Mesh OM5 PAC serves as the robot's Wi-Fi radio. This is like any other wireless access point that you might have. So the one in your home, the one at school, it's just a little wireless router. It's nothing particularly special. It's just tiny. It can be powered either through the barrel jack or via power over Ethernet. Most teams these days use power over Ethernet because it's a latching connection. The barrel jacks tend to fall out very, very easily for some reason. And so teams have shied away from it. And there are very easy to implement PoE injectors that enable you to use the same Ethernet connection that you would to use to communicate with the RoboRio to also power the device. As you can see in the slide, I have very little good to say about this thing. I really don't. This is the one thing where I'm gonna break the teacher character and be like, this thing is I was really hoping that with the Rev control system upgrade, which just recently came out, they were going to replace these. According to a recent blog, and this was recorded on 6/14/2022, for those that may be watching this later, according to a recent blog, they were looking at trying to replace this maybe for the 2024 season. But given the way the blog was worded, it sounded like they didn't have a definitive way forward that they were getting ready to test. So my assumption is that, and this is an assumption warning, my assumption is that they probably have an RFP out or something to their vendors to see if anyone can produce something better. Frankly, the thing that came before this was drastically better. It was a D-Link router. It had 4 Ethernet ports rather than just 2. Really, the only thing that it did not support that would be nice to have was power over Ethernet injection. But generally speaking, I had no issues with those, and they could have sticked around if they would. I mean, these have had so many problems, and they're so difficult to deal with, and yeah. But either way, that's my rant. Hopefully we'll get something different soon, but for now, your general interaction with the robot radio will be very limited because it's supposed to be a plug and play device. Like, you image it and then you just plug it in and it should work. It doesn't always happen that way, but since its inception, it's gotten better. It's still not great, though. Final thing that we're going to talk about for general electronics is batteries and the main breaker. All of FRC uses very specific robot batteries. They're 18-ish amp hour sealed lead acid AGM batteries. You don't necessarily need to know what that means, but they look like big Power Wheels batteries if you ever had a Power Wheels when you were a kid. They don't last very long running on a robot. Usually about 1 match is all they'll suffer through, and then they're basically dead. There are no other options for power in FRC. You have to use these batteries, and it is for a good reason. These batteries get poor treatment compared to what they might get in other applications. and they handle it very well. I have seen students carry batteries by the wires. I've seen students drop batteries from chest height onto concrete floor and watch them swell but not explode. And I wouldn't be able to say the same thing about, you know, lipo batteries or LifePo batteries or anything like that. These batteries have proven that they are a safe solution to have around high school students who do not understand how dangerous batteries can be most of the time. Um, with that being said, between the battery and the PDP or the PDH, you will always have a main breaker. This is used to turn your robot on or off. The main breaker has a 120 amp limit, meaning you can pull 120 amps through it. Again, that's a more significant conversation about electronics in general to be had later. But it can maintain this for about 2 seconds before it will pop. It's heat based, so you got to get it hot to make it pop. And of course, as the temperature goes higher, the faster it will pop. Your breaker has to be very visible on your robot. If someone needs to run out onto the field after everything has been e-stopped and shut your robot off, it should not be difficult for someone to find where your button is, specifically the big red button on the top. The only other thing that I will say about the main breaker is that they tend to be relatively difficult to pop, but they can be popped. And you'll know when they pop because the snap sounds a bit like bones breaking. It's quite loud and it's very clear when it happens because it's a very, very loud, audible click noise. So I don't know that we as 2648 has ever popped one. 6172 had some custom gearboxes that they made that had 3 sim motors each, and we are about to talk about motors in just a second here. And that robot drove forward and back great, but as soon as you tried to turn, all of those sim motors hit their stall current and pop goes the weasel. Loud snap noise. With that being said, again, we're going to take another pause for questions. Are there any questions? I would say none. So let's keep going. All right.
You need to get like Jeopardy music just like ready to go in the background.
I said last week in the after show, I think, that I needed a stream deck.
Oh yeah, I
extra
think
cricket noises.
I did, and I just don't really want to spend the money on a stream deck. I'm thinking about buying, and this is way off topic, but I'm thinking about buying a Prusa 3D printer, and I'm skittish about spending that much money, and I don't necessarily need to spend more at the moment.
You
There's
should
a
get like
soundboard.
actual live crickets and open like the bin of them each time.
Have pet crickets just lying around.
All right. So the next thing we're going to talk about is motors. For the most part, in FRC, we use some variation on the 12-volt motor. We can now use, it hasn't always been this way, but we can now use both brushed and brushless motors. Brushless ones have been around for a little while. Brushed ones have been around forever. Many teams have started to move towards using more brushless motors. They tend to weigh less and provide the same or better performance. But brushed motors do still have their place in FRC, especially given the fact that the motors themselves and the motor controllers used to control them, depending on what you buy, tend to be less expensive. So the barrier to entry of using them tends to be less. The first types of motors that we're going to talk about is the SIM family. The SIM motor has been around for many years in FRC. I remember seeing on the first robot that I participated in when I was a freshman. It was basically all the big sims type thing. Um, but over the years, two other motors were added to the sim family. These were the mini sim and the bag motor. Uh, you will find that most gearbox solutions and most other motors in FRC use very similar or the same hole patterns, mounting hole patterns to the sim, simply because they were so ubiquitous for so long that so many gearboxes were designed around them. And to keep things simple and compatible, many motors and gearboxes all use the same sort of hole patterns that come from the sim family. Um, there are motors similar to sims, specifically like mini sim bag motor area, like the 775 Pro and the AnyMark Redline motors. Those motors tend to fill performance holes where none of the sim family kind of lines up. Their hole patterns are different, and they have different gearboxes because of that. Obviously, you can use some of the same gearboxes with adapters, but um, uh, they serve as kind of the gap fill as far as brushed motors are concerned, because the sim family is brushed, um, to sort of fill in the space where there isn't a sim to take up a certain need for speed or need for power type of thing. The next motor family that we're going to talk about is the Neo family. Neo motors were the first general use, and I use the term general use because there was a brushless motor before the Neos, but the first general use brushless motors in FRC. The regular Neo and the Neo 550 provide similar performance to a full-size sim and a bag motor, but they are lighter weight and they have slightly better performance depending on how you look at it. One of the nice things about the Neos is because of the fact that they're brushed motors, they do have integrated encoders. So measuring the distance traveled of a system or measuring the rate of rotation of a system is relatively easier to do with a Neo, simply because you aren't having to try to mount an additional encoder to a system to try to measure those things. One thing to mention, though, is Neos can be cost prohibitive for some teams. The motors are slightly more expensive when compared to something like a full-size sim or a bag motor. But really where things start to hurt is when you look at motor controller options, which we'll talk about in a little bit. You can get some relatively cheap motor controllers that will be able to control a sim. But in order to control a Neo, there's really only one name in the game, and it's comparatively more expensive type of thing. Per motor and motor controller set, it's more money than it would be if you were buying just a sim and its associated motor controller. The next thing that we're going to talk about is the Falcon 500. This is Vex's answer to the Neo motor. Falcons have become popular because they have both an integrated encoder and a motor controller built in, all one piece. So you don't actually have to buy a separate motor controller to make this work. Another nice thing about the Falcons is they have replaceable output shafts. So if, for example, you needed to cut down a shaft to work with a particular gearbox for one season, the next season you could just buy a replacement shaft, pop the old one out, put the new one in, and you've got a full-length shaft again without having to buy a whole new motor. According to Rev's data, according to Vex's data, excuse me, this motor has the best power to weight ratio at 20 amps in FRC. Obviously, that's Vex's data. I don't expect them to lie, but it would need to be corroborated by somebody who is not, into trying to get more Falcons sold, kind of thing. The Falcons are very commonly used for swerve drivetrains along with the Neo motors. Again, probably simply because of that power to weight ratio. But of course, again, the Neos and the Falcons both have a relatively high cost to implement when compared to sim family brushed solutions. The only other thing about the Falcons is that if by some chance you burn up the motor controller or the motor, you're out both. You can't replace the motor controller and you can't replace the motor separately like you would with any other solution. For some teams, this isn't a problem because they design their mechanisms such that they know what its limitations are, and they ensure that the motor is up to the task of doing what needs to be done, and so the likelihood that it will burn out is relatively low. But of course, if you don't have that forethought and determination of, yes, this is going to work and not let out the magic white smoke, then you could run into trouble, especially with cost and trying to keep spares on hand, because again, buying it as one whole singular unit tends to be a fairly high upfront cost. So just something to keep in mind there. There are tons of other motors that you can use in FRC. Tons may be the wrong word, but there's a lot more than we could talk about easily in an evening type of thing. To name a few: Bosch seat motors, Dynamo brushless, window motors, Never Rest, PG gear motors. There are all kinds of different motors, all for different applications. We as a team have used a lot of window motors for things. We've used seat motors before. It all kind of depends on what you can get your hands on easily. And these motors tend to have decent high torque outputs with relatively easy mounting options. Specifically, Bosch seat motors and window motors in particular tend to be pretty easy to find and pretty easy to put on a robot. So this ends the motors section. So I will pause again and ask for any questions. We still have a little ways to go, but we'll probably be finished around 7:10. This one was always going to be a little bit longer. So are there any questions? All right. So now we're going to talk about motor controllers. Motors by themselves can't really be used in FRC. They always have to have a motor controller in between the power distribution panel or the power distribution hub and the motor itself. Motor controllers are how we control the speed of motors. And what they do is they vary the amount of voltage and current given to a particular motor to change its potential amount of output speed and power. Most motor controllers in FRC these days are sent instructions via CAN, but there are some that are still available for use that rely on PWM. There are many types of motor controllers available to teams. Some are more smart than others, and we're going to go over different ones over the next few minutes. But generally speaking, the overall performance of a motor controller is roughly the same these days. It all depends on what the additional features you want to use and what type of motor you want to drive, because not all motor controllers work with all types of motors, specifically the difference between brushless and brushed motors. So the first motor controllers that we're going to talk about are the Victor SP and the Victor SPX. The Victor SP was a motor controller that only used PWM speed control, whereas the SPX can use both PWM and CAN, and the SPX is what is pictured here. If you actually ever look at my robot, because I was trying to build my robot as cheaply as possible, I bought Victor SPs when they still existed. They are no longer sold, but the Victor SPX is still one of the cheapest motor controllers in FRC, and its price looks to have been lowered slightly to try to take up what space the Victor SP left behind, because the Victor SP was very inexpensive. I think I paid $40 per motor controller, which is quite low. The nice thing about the SPX is it has onboard PID control support, as well as other advanced features that help remove load from the RoboRio. And you'll see that as a common theme as we talk about some of these other motor controllers, that they tend to have additional features that would remove work from the RoboRio by using the commonly connected CAN bus to communicate with other controllers to coordinate actions and motion without the RoboRio having to do a lot of the math and grunt work to make that happen. So the next thing is the Talon SRX. The SRX is a high-end, well-featured motor controller. It is used for brushed motors, and I should have mentioned previously too that the Victor SP and the SPX are only for brushed motors, as is the Talon SRX. The SRX supports multiple different communication profiles: PWM, CAN, SPI, and serial. For the most part, you're going to see teams using these with CAN. The nice thing about the SRX is that not only does it have onboard PID control, but it has its own expansion port, so that you can actually connect sensors directly to it and have the controller inside the motor controller read those sensors and perform motor-based actions based on those sensors. For many team implementations, the difference between an SPX and a Talon SRX is simply cost. And I'll rephrase that to say mid-tier and lower teams is simply cost. Some of the high-end control features and the availability of that extra sensor port on top of the SRX pushes some teams to lean more on those, simply because it again takes some of that load off the RoboRio. Next, we're going to talk about the Spark Max. The Spark Max is the first general use brushless motor controller in FRC. The Spark Max can control both brushed and brushless motors. And it has similar features to the Talon SRX. So it has that top port for additional sensor I/O. It has the ability to do onboard PID control. And the Spark Maxes specifically have an extra port that allows for plugging in the encoder connection from a Neo motor, so that way the Neo motors function properly. Now, the Spark Max is the one motor controller that you're going to be able to get to work with a Neo motor. It's possible that if you found a non-compliant, like non-FRC compliant brushless motor controller, you could make it drive a Neo motor, but I generally wouldn't recommend it, simply because they're designed to be together, one cohesive unit. Again, the Spark Max is mostly controlled by CAN, but it does support PWM as well. I'm not quite sure about SPI and serial, but again, the vast majority of teams are going to control something like this with CAN, and for those that don't, they'll probably fail back to PWM. Very quickly, let's talk about some obsoleted motor controllers. There are many motor controllers in FRC that are now considered obsolete, either because they aren't sold anymore or their feature set is diminutive compared to what we have today. Many of these motor controllers, though, work just fine still, but they're not worth the additional weight and wiring complexity. Specifically, these motor controllers are mostly PWM, which requires a lot more wires to be run from the Robo Rio to different places to be able to communicate with these motor controllers and tell them what to do. However, if a team has a bunch of these or has access to these, they're perfectly fine for off-season projects and demo robots. More than likely, when I finish rebuilding the Frisbee shooter will be Sparks now, but some of my ideas that I want to try to implement may include the use of Victor 888s, which is the motor controller bottom left, and they work perfectly fine. They're just kind of clunky. They require a fan. They're PWM only, and they're just a bit in the way. But for an off-season robot that I use for demos, it doesn't really matter because I'm not necessarily looking for performance or the ability to win a competition. I just want something to work, type of thing. All right, we are done with motor controllers. I believe I have one section left. Are there any questions about motor controllers?
You talked about the Talon SRX and other more advanced controllers. You said that they have PWM, CAN, and SPI, whatnot. Does it automatically tell when you send it signals what sort of signal that is? Like one of the CAN, PWM, whatnot.
So I am not sure how the SPI works. However, CAN works the way it does because it requires both wires. Whereas with PWM, I believe it's the green wire that is held to ground, which indicates to the controller that the yellow line should be a PWM signal.
Oh, okay. Yeah, that makes sense.
I'm not quite sure how SPI works. My assumption is that one line is SICK, S-clock, and one line is MOSI, master out, submitter in type of thing. I'm not sure though, because again, I honestly am not aware of any team that has actually used the SPI functionality of any of the controllers. I don't even think that it's actually first legal to use the SPI functionality. Cross the Road Electronics has their own robot control, like robot controller, like beyond the Robo Rio. It's called the Hero. And I assume that the SPI functionality can be used in some way with that. But I don't believe that it's first legal to use SPI to control a motor controller, even though it is available.
SPI wouldn't be very practical for motor controllers anyways.
It would certainly be very difficult once you started juggling all of the chip select lines to try to manage all of those different connections. I'm certain that if they're using it on the Hero, each expansion port on the Hero probably has its own chip select or subset of chip select lines that you can use. But again, I don't own a Hero and I've never actually tried figuring it out because it's never been a problem. Any other questions? Okay. So the next thing we're going to talk about is sensors. We've kind of poked and prodded at sensors, especially when we were talking about the different ports on the Robo Rio at the beginning of the session. Sensors, if motors are the way that you interact with the world through your robot, then sensors are how your robot actually sees the world. There are a lot of different types of sensors. We aren't going to go over all of them tonight. We will go over a lot of the common ones, not particularly in depth. some of the common ones, we could have 20 to 30-minute long conversations about each of them, which I am not prepared to do this evening. But to put it generally, sensors tend to follow human senses because that's what we can think about. Touch, sight, hearing, balance, that sort of thing. There are some sensors that take those things to an extreme. So for example, time of flight sensors tend to use ultrasonic sound. So we wouldn't be able to hear it, but the sensors can hear it. And like I said, we're going to talk about some of the more common sensors very briefly for each type. And then if there's questions at the end, I can try to answer some specific questions if they're there. So the first type of sensors that we're going to talk about are buttons and switches. Probably the most simple type of sensor that we could feasibly talk about. Best way for sensing contact between two surfaces. So if you want your robot to like back up and turn when it hits a wall, a button can do that for you. Buttons are hooked up using digital inputs and provide on or off signals. Either the button's pushed or the button's not pushed. And again, some examples include detecting contact with an object or sensing when a mechanism like an elevator is at the top or the bottom of its track. So you wouldn't necessarily want to continue running a motor. Let's say if an elevator was all the way at the bottom, because you might snap whatever cable was pulling the elevator up and down, or you might burn out the motor. So that would be one application type of thing. Potentiometers are used generally to measure angles based on a change in voltage when something turns the dial on the potentiometer. The example that I gave earlier was a volume knob. Potentiometers use analog input for sensing because it needs to be able to output a voltage to the RoboRio to indicate a particular angle. That voltage is taken and some math is done to figure out exactly what the angle is. Most, I won't say all, but most potentiometers tend to be limited to a certain number of degrees that they're capable of turning. And a robotics-based example of what a potentiometer might be used for is, like I said earlier as well, if you had a robotic arm, an encoder, which we're about to talk about, you may not be able to get quick and easy measurement with an encoder unless you do take some serious care with how you're getting those measurements. Whereas a potentiometer is a very simple system that's already designed to be able to provide an angle based on a voltage. So that might be the better solution depending on what you're trying to do. The next sensor is the encoder. Encoders are used to measure the rate at which something rotates and how far something travels. So you can either get speed or you can get displacement, how far you've gone from point A to point B. Most encoders will use 2 or 3 digital inputs to sense distance traveled, rate of travel, and direction of travel. There are some encoders that use connections like SPI to communicate with the RoboRio. They aren't super commonly used. Normally you'll see an encoder connected either via CAN or via digital inputs. And probably the most common use for an encoder is measuring the distance traveled by a drivetrain. So you'd have an encoder on both sides of your drivetrain, and it would measure independently how far each side of the drivetrain traveled. And you can use that information to go a particular distance, to travel at a particular speed, similar to how a car might with cruise control traveling at a particular speed. The next thing that we're going to talk about is gyroscopes. Gyroscopes are used to measure rotational acceleration. And from that information, you can calculate rotational velocity and the current angle of the robot. This gyro depicted here I do not know off the top of my head, but there are some gyros that will do that calculation for you. And you can actually request from them either the acceleration, the velocity, or the angle. But I believe this one just provides the RoboRio with an angle, and then the code written for the RoboRio does the calculation of velocity and displacement of angle. Generally speaking, gyroscopes will use a communication protocol like I2C, CAN, or SPI. The one depicted here is the SPI one that I said goes in the upper right-hand corner of the RoboRio. Gyros tend to be used for figuring out which way your robot is facing on the field. And that's generally it. You could use a gyroscope to figure out what angle an arm is at, but at that point, you're over engineering an uncomplicated problem kind of thing. So part of understanding sensors is knowing when certain sensors should be used and when certain sensors shouldn't. The next sensor that we're going to talk about is an accelerometer. Accelerometers are similar to gyroscopes, but they measure linear acceleration. So rather than rotating forward, left, right, up, down, that sort of thing. And again, it's a measurement of acceleration, so something has to do the calculation to figure out the linear velocity, and ultimately from that, the distance or the displacement. Again, accelerometers tend to use something like I2C, CAN, or SPI to communicate with the RoboRio. And in fact, the RoboRio has a built-in accelerometer. Generally speaking, by themselves, accelerometers aren't used very often, but in tandem with gyroscopes and some clever math and a lot of filtering, you could feasibly create a system that tracks the relative position of the robot while it's running, like without encoders. That particular project is outside the scope of this conversation, but it is something that could be done. It's a lot of work, but it is something that could be done. The next sensor that we're going to talk about is cameras. I should not have to explain what cameras are. Generally speaking, you can use basically any standard USB webcam with the RoboRio. And some cameras, like the Limelight depicted here, can actually connect to the robot's network through Ethernet, a regular network connection. A lot of the reasons why teams will put cameras on their robot is to track the reflective tape targets on the field, so that they can vision track and use that vision tracking information to guide their robot to specific places on the field. In recent years, in particular, the Limelight, which, like I said, was depicted here, has become pretty ubiquitous. It's very easy to implement vision tracking with the Limelight, and it doesn't require complicated code to retrieve the information of what the Limelight is seeing. There is some inflexibility with the Limelight, and there are other projects, other operating systems that you can run on the Limelight, because the Limelight is basically just a Raspberry Pi in a box. There are other operating systems that you can run on the Limelight that provide other features, but generally speaking, most teams just run the regular Limelight software and don't have any problems. This section was also going to talk about LiDAR. LiDAR is a range finding mechanism that uses light to measure distance in a multitude of directions, and is used by a few teams to help with robot guidance on the field, especially when doing very autonomous heavy tasks with their robot. It's not super common because LiDAR modules tend to be on the high range of expense. And there's really only a couple of modules that fit within budgetary constraints for teams. So I elected to remove it and just kind of give it an honorable mention towards the end of the discussion about cameras. But with that, we are finally done. So are there any questions about sensors? All right. So with that, this has been basic robot electronics. Hopefully I've given good information. Hopefully nothing what I said was wrong. But once I make this public, if I did say something wrong, someone will correct me and I'll put a blurb or something in the video. This week there is no challenge, so get caught up on other challenges. And I will post a link that is it'll be a download link to my Dropbox this week, because I don't need people from outside getting into my GitLab server, because I don't think my VM could handle it. But you'll be able to download a PDF copy of this presentation, and of course this will get uploaded to YouTube once I've had the opportunity to trim it, and make it slightly nicer, and make sure that all the crap on the beginning and the end is cleaned off.